Jacobi iterative method and explain how we can use this method to solve a linear system of equations of the shape of ax equals to b. Let's first understand what Jacobi method is. Jacobi method is the simplest iterative method for solving a linear system of equations, n equations with n unknowns. Mainly, this method is an iterative method to solve these linear system of equations starting from an initial condition, and this initial condition could be random. After a number of iterative steps, this algorithm or this method can reach out to the specific numbers or the specific solutions of these linear system of equations. Now, for this method to work, these linear system of equations should be diagonally dominant. So this is the condition for these linear systems to satisfy in order for this method to work. Now let's explain what diagonally dominant means. Suppose you have these n linear system of equations with n unknowns starting from x1, x2, ending to x of n. Now let's put these equations in the form of ax equals to b. Now what's A? A is the matrix of the coefficients of the unknowns. So if all of these purple coefficients represent the square matrix A. So A is the matrix of the coefficients of the unknowns. X, however, is the unknowns that we have. So the unknowns starting from x1, x2, all the way to x of n equals to b. Now b is the right-hand side of all of these equations, b1, b2, ending to b of n. Now, to understand what diagonally dominant, we need to look at matrix A. Matrix A should be strictly dominant diagonal matrix, and if this condition is satisfied, we can use Jacobi method to solve these systems. Now, what do I mean by strictly dominant diagonal matrix? Let's take this matrix, and in mathematics, a square matrix is said to be diagonally dominant if for every row of the matrix, the magnitude or the absolute value of the diagonal entry in a row is larger or equal than the sum of the magnitude of the other non-diagonal entries in that row. So for example, in the first row, the diagonal element is A11. In the second row, the diagonal element A22. The final one, the diagonal element is ANN. So let's start row by row. Let's take the first row and and we need to test whether the absolute value of the diagonal element, which is A11, is larger or equal than the rest of the off-diagonal elements, or the absolute values of all the other non-diagonal entries. We need to do that for every row of this matrix. We need to check if each row satisfies this condition. If each row satisfies this condition, then this matrix is said to be diagonally dominant. All right, I think it would be better and helpful to put all of these abstract ideas into an example. All right, let's give this example. We have three equations with three unknowns, x, y, and z. So the first equation is 4x minus y plus z equals 7. Second one, 4x minus 8y plus z equals minus 21. And the third one is minus 2x plus y plus 5z equals 15. We need to see if we can, or if Jacobi iterative method can be used here to solve these three equations. First of all, we need to check if these three equations are diagonally dominant. Let's put them in the ax plus b form. So the a here is the coefficients of the unknowns. So for the first equation is 4 minus 1, 1, which is the first row. The second one is 4 minus 8 and 1, which is the second row. And the last row, which represents the last equation, is minus 2, 1, and 5. The x here is the vector of the unknowns, so the unknowns that we have here is x, y, and z, and the b is the right-hand side. So the right-hand side here we have 7, minus 21, and 15. All right, let's take matrix A. The diagonal entries of matrix A are 4 for the first row, minus 8 for the second row, and 5 for the last row. All right, so we need to check now, is the absolute value of 4 larger or equal the sum of the absolute value of the of diagonal elements minus 1 plus 1? Well, for the first row, this is satisfied. Let's go to the second row. The diagonal element is minus 8. The absolute value of minus 8 is 8. Is it larger or equal than the rest of the off diagonal, which is 4 plus 1? Well, that's also satisfied. The last one, the diagonal element is 5. Is it larger or equal than the absolute value of the sum of the off diagonals? Well, yes, because 2 plus 1 is 3 and 5 is larger than 3. So I can say that this system of linear equations is diagonally dominant, and we can use Jacobi method to solve the system. Let's do a trick and let's swap the first equation with the last equation. We didn't do anything fancy, so we used exactly the same 3 equations. However, we just swapped the last equation, we put it as the first, and the first we put it as the last. And let's check now if the system remains diagonally dominant. All right, let's put it as ax equals to b again. So a is the coefficients of the unknowns here. So a is different now, so 2 rows are swapped. And x is the same, and b also the first row and the last row are swapped. Okay, let's check now matrix A. Now we have the diagonal elements here are minus 2, minus 8, and 1. So for the first row, we have minus 2. The absolute value of minus 2 is 2. Is it larger or equal than the sum of the absolute values of the off diagonals, which is 1 plus 5? Well, 1 plus 5 is 6, and 2 isn't larger than 6. So that's the condition is not satisfied for the first row. All right, let's check the second row. Is the absolute value of 8 larger or equal than the sum of 4 plus 1? Well, that's satisfied. Good. Let's go for the last one. Last one is the absolute value of 1 larger or equal than 4 plus 1. Well, also this is not satisfied. So I can say that this system is not diagonally dominant. So just by swapping just 2 equations of the system, it can change everything about this system, or solving the way we solve this system. All right, so we need to code this. We need to write a MATLAB code to explain this. Let's move to MATLAB now. And I will be using exactly the same 3 equations that I used in the PowerPoint. So I will use the 3 equations that resulted in a strictly dominant diagonal matrix A, and when we swap the first and the second one. All right, so very first step, I'll start with the first one, when the matrix A is diagonally dominant. So as always, we need to start our code with clear all, close all, and CLC. Close all will close all opened plots or figures. Clear all will clear all previously assigned variables. CLC will clear your command window. So this will declutter your code window or your code environment. All right, so let's start first with defining an initial guess. So we said that if we want to use Jacobi method to solve these 3 systems of this system of 3 equations, then we need to start with a random guess. So let's define an initial guess of the 3 solutions. So the first one, I'll say x1, for example, 13. So it's a very random number. For y, for example, I'm gonna say it's minus 5. For z, I'm gonna say, for example, it's pi. So these numbers are completely random, and we need to see, or we need to test Jacobi method or Jacobi algorithm if it can converge these three initial conditions, initial guesses to the actual solutions. All right, now we need to do the iterations. So here, go through the iterations. All right, let's go for 4. J goes from 1 to, I don't know, let's go for 10 iterations. Okay, let's close the end statement here. All right, first of all, we need to get x from the first equation, and then we need to get y from the second equation, and then we need to get z from the third equation. So x1 from the first equation, which is j plus 1, I need the next value of x. So if I calculate this, I will say this is 7 plus y1j minus z1j over 4. This is what we solved the first equation for x. Let's solve the second equation for y now. So j plus y equals 2. So for the second one, it's 21 plus 4 times x1j, and then plus z1j, and all of these should be over 8. And now I think here we have, so it's times here. Okay, let's solve for z for the third equation. So it's 15 plus 2 times x1j and minus 1 y1j, and all of these I'm going to divide them by 5. All right, so this is the 3 equations. I solved x, y, and z for these 3 equations, and I'll let the iterations go and see if they will converge. Let's see if they will converge. So let's plot the solutions. All right, so let's go for example, figure, and let's go for subplot 2, 1, 1. There is a reason why I'm using subplot. I'll explain that later. So let's plot all of them. So I need first a range on the x-axis. Since I'm going through 10 iterations, I'm going to set the x-axis to have 11 points. So I want to show x1, and let's show it in blue. And I want to show y1 as well, and let's show it in red. And I want to show z1 as well, and let's show it in green. And let's do a line width here, which is, I don't know, 1.5. All right, so the x label in this case will be the number of iterations, and the y label here, it will be the actual solution. Yeah, that's it. Let's run it and let's see what we get. Will the Jacobi method converge to the actual solutions? So if I enlarge this, you can see here that the Jacobi method started with the initial guesses that I gave it, which were completely random, and after a couple of iterations, until I am at 5, I think, after 5 iterations, after the 5th iteration, the Jacobi method actually gave the actual values of x, y, and z, and you can see here. So that, for example, x is, so what's, sorry, it's x1. So what's x1? So x1 converged at the end to 2, which is, so x here is the blue one, so it's 2. And for example, y, let's go for y end here, it's 4. And x1 end it's 2, and z1 end is 3. So these are the solutions actually of this system of equations. X is 2, y is 4, and z is 3. All right, Good. So it's working. Now let's go and see if this keeps working if we have a non-strictly diagonal element, matrix. All right, so these are the equations of the non-strictly diagonal, dominant diagonal matrix, and I will do exactly the same thing. So I will start with initial guesses. So now I have x2. x2 is for the second system of equations. I'm gonna put like, I don't know, 13. I'm gonna use exactly the same random guesses actually. This is minus 5, and I think for z2 we used pi. Okay, so let's do the iterations here. And let's go for the same number of iterations. So I have 1 until 10. Let's end it. And let's go equation by equation and solve for these equations. All right, so for the first equation, let's solve for x. So x2 j plus 1, it's equal to, I have minus 15 now, plus y2 j plus 5 times z2 j, and all of these I will divide them by 2. This is x2, y2, which is j plus 1. It's equals to 21 plus 4 times x2j, and then I have plus z2j, and I need to divide all of this by 8. So I'm solving y for the second equation. Let's solve z for the third equation. So z2j plus 1 will be equal to 7 minus 4 times x2j plus y2j, and I think that's pretty much it. Okay, so now I'll let the iterations go, and I need to make sure, will they converge? All right, let's plot them. So let's plot the solutions here. I am going to use exactly the same figure. I'm going to add hold on here, and I'm going to use the second subplot, which is 2, 1, 2. And I am going to, well, they are exactly the same thing as here. However, here I have x2, and here I have y2, and here I have z2. Remember, we didn't do anything, we just swapped them. So if we swap them, it's not big of a deal. So we should end up with x2, y4, and z3. We should get that. Will we get that? All right, let's run this and see if we would. Well, that's interesting. So we started with our initial here, but you can see here on the y-axis, it's to the power of 5. So they totally diverge, all of the variables, x and y and z. And again, this is because the second system of the equations is not diagonally dominant. Once the system is diagonally dominant, Jacobi method works perfectly after just 5 iterations. However, here, even if you carry on after 11th, they will never ever converge. Okay, that's it really. If you have a better way to code this, let me know in the comments. I will add the GitHub link that includes the code that I used here in the MATLAB in the description box below. Hopefully this is helpful. Thank you very much, and I'll see you in the next video. Thanks.